Inside a brightly lit laboratory room, a robotic arm slides along a metal rail above a row of glass reaction vials, while a computer monitor beside the bench shows a live graph updating every few seconds. In rooms like this, machines run scientific experiments day and night, while software studies the results and decides what experiment happens next. Cameras watch liquid levels inside the vials, pumps push precise drops of solvent through narrow plastic tubes, and software on a workstation decides what experiment should happen next based on the previous results. When people talk about AI scientists working 24 hours a day, they are usually referring to systems like this where machines run physical experiments, while an AI model studies the data appearing on the screen. In a traditional materials research lab, a human researcher wearing safety glasses stands at a bench measuring powders on a digital scale, pouring the powders into a small crucible and placing the crucible into a furnace that heats up with a glowing orange coil. After hours of heating and cooling, the researcher removes the sample, inspects it under a microscope, and records the result in a notebook before the next attempt begins. Each test can take half a day or more, and every mistake means repeating the same steps again. Because the process is slow, a small research team might test only a few hundred material combinations in an entire year. That pace becomes a serious bottleneck when scientists search for new battery materials, heat-resistant alloys, or catalysts that improve industrial equipment. The challenge becomes obvious when you imagine a large table covered with jars of different powders, each jar labeled with a chemical symbol and stacked in neat rows across the room. Every possible mixture of those powders might produce a slightly different material once heated and cooled inside a furnace. Even with a few dozen starting ingredients, the number of combinations quickly climbs into the millions. A human research team cannot physically mix and test that many samples, so the researchers rely on educated guesses about which mixtures might work. Many promising possibilities are never tested simply because there are not enough hours in the day to prepare every sample. Please subscribe. Autonomous laboratories attempt to solve that bottleneck by connecting three physical systems inside one room. First, robotic equipment handles the physical tasks a technician normally performs, such as pipetting liquids, weighing powders, and transferring samples between machines. Second, measurement instruments like spectrometers, microscopes, and electrical test rigs record how each material behaves when current flows through it or when heat spreads through it. Third, an AI model running on a nearby server analyzes the measurement data and proposes the next experiment. When the robotic arm receives the instruction on its control screen, the arm immediately begins preparing the next sample without waiting for a human researcher to return the next morning. A good example of this approach appears at Lawrence Berkeley National Laboratory, where an automated system known as a materials acceleration platform combines robotic sample handling with AI analysis software. Inside the facility, racks of sealed containers hold thousands of chemical ingredients, while robotic dispensers measure tiny amounts and deliver them into reaction trays. As each tray moves along a conveyor into an analysis station, cameras and sensors capture data about crystal structure, conductivity, or thermal stability. The information travels through a network cable to a computer cluster that updates a model predicting which combinations might produce stronger battery electrodes or faster semiconductor materials. Another major research effort is taking place at Argonne National Laboratory, where automated beamlines connect high-powered measurement equipment to AI-controlled experiment schedules. A robotic sample holder slides thin material wafers into a chamber, where a narrow beam of light scans the crystal structure. Each scan generates a detailed image on a large monitor in the control room, showing patterns that reveal how atoms arrange themselves during synthesis. Instead of waiting weeks for scientists to analyze the images manually, AI software compares the new patterns against thousands of earlier results and immediately suggests adjustments to temperature, ingredient ratios, or processing time for the next batch. The speed difference becomes clear when you compare a normal research cycle with an automated one. In a conventional laboratory, a scientist might spend several hours preparing a sample, another hour heating it in a furnace, and several more hours running measurements before entering results into a spreadsheet. In an autonomous lab, the robotic system prepares the sample in minutes. The furnace program starts automatically, and measurement data flows directly into a database. As soon as the data appears on the screen, the AI algorithm evaluates whether the material met the desired property, such as electrical conductivity or mechanical strength, and immediately launches the next experiment. Machines working around the clock introduce new technical challenges that are visible on the lab floor. Pumps must deliver exactly the right volume of liquid. Tubing and valves need constant calibration to prevent drift. Robotic arms must grip delicate sample trays without dropping them onto the steel bench below. Temperature sensors inside furnaces must remain accurate, because a difference of only a few degrees can change the structure of a material completely. When something fails, technicians might walk into the room the next morning and see halted machines with warning lights flashing on the control panels. The economic trade-offs also become visible when you look at the equipment filling the laboratory. Robotic systems, precision pumps, and automated measurement instruments can cost millions of dollars to install, and they require technicians who understand both mechanical systems and software. However, once the equipment is running reliably, it can perform thousands of experiments every month without stopping for weekends or holidays. That constant operation allows research teams to explore much larger sections of the chemical search space than a small group of graduate students working daytime hours could ever manage. There are also physical limits that no amount of automation can eliminate. Even if an AI system proposes a promising new material formula on a computer screen, the atoms inside that material must still obey the laws of chemistry and physics when the sample is synthesized in a furnace or reactor. Some materials cannot form stable structures at ordinary temperatures, and others may crack or degrade after repeated use in real equipment. When researchers test a new battery compound or semiconductor wafer, they often run long stress tests inside climate-controlled chambers to see how the material behaves after months of heating, cooling, and electrical load. Despite those limits, autonomous laboratories are already changing the pace of energy technology research in visible ways. When a new battery material appears promising on a graph showing charge capacity and cycle life, engineers can quickly move from laboratory samples to prototype cells assembled on a factory-style test line. In another building down the road, technicians wire the prototype cells into a rack of power electronics that charge and discharge the cells repeatedly, while sensors record performance on wall-mounted displays. The faster scientists can discover and test new materials in the lab, the sooner engineers can evaluate whether those materials will survive real operating conditions inside vehicles, data centers, or electrical storage systems. What makes this shift significant is not that machines have replaced scientists, but that the physical laboratory itself has become part of a continuous feedback loop between machines and people. Researchers still walk through the lab wearing safety glasses, checking instrument readings on control screens and adjusting equipment when something behaves unexpectedly. But instead of performing every step by hand, the researchers supervise a system that runs thousands of experiments automatically while AI software analyzes results in real time. When the robotic arm starts another experiment late at night and the data graph begins rising on the monitor, the laboratory is still working even though the human team has gone home for the evening. Thank you very much for watching. Please like and subscribe.